In this video, we are going to measure the capacitance of a capacitor. We're going to use two different methods. We're going to charge and discharge the capacitor. But first, let's find out what the capacitance is supposed to be. Now, the capacitor itself says that it is a 4,700 microfarad with a maximum of 12 volts by a company called 𝗟𝗶. And it has not much more information on it. We know that it's designed to vent before it explodes, if wired incorrectly, and the temperature range from -40 to 85 degrees Celsius. But I just so happen to have found exactly the same capacitor on this website. Not sure if that's going to be coming through clearly enough on the screen, what with the horrible interference effects and all, but it's as good as we're going to get. And it says on this website that the capacitor has a tolerance of 20%. So that's something I can reference. I know what I'm expecting the capacitance to be within 20%. So here I have written down the reference, the full URL with the access date of how I found out this 20% tolerance figure. And I also noticed that this is an electrolytic capacitor. When we look at it closely, we can see that there is an indication that we have to connect this terminal to the negative potential and this one to the positive potential, so that the current flows through it this way, so that the electrons flow through it this way. You'll also notice that there's a shape to the case. It sort of dimples in at the positive end. This is the positive end, this is the negative end. That's really important, because if you connect an electrolytic capacitor up back to front, then it will fail. And one of the ways it can fail is explosively. So what we're going to do is we're going to connect up a simple circuit for discharging and for charging. Let's start with discharging. I think I spelt that right. The simple circuit is going to have some power supply, which will be connected to our capacitor in such a way that we can disconnect the power supply. So we'll have to use a single pole double throw switch like this. Then that is going to be connected in parallel with a voltmeter and in series with a resistor, so that we charge the capacitor by switching this switch to the left, and when we switch the switch to the right and start a stopwatch at the same time, we record the potential difference across the capacitor as it discharges through this resistor. Now, we are going to want to be able to measure these values, so we want a good enough time constant in order to be able to actually measure the potential difference across this capacitor at different times, which means we need a large enough resistor. Now, given that this is 4,700 microfarads, I'd be thinking something in the order of, let's say, 5,000 to 10,000 ohms would give me a large enough time constant that the potential difference would drop slowly enough that I can actually measure it at different times. And it just so happens that I have a resistor. Now, unfortunately, it's mounted on one of these horrible boards. It's a 10,000 ohm resistor. It claims to be 10,000 ohms, but we need to check that. And there's two ways we can check that. The first way we can check that is by using the resistor color code. And the second way we can test that is by using a multimeter. So it says it's 10,000 ohms. Let's just whip the multimeter out and shove it in like that. And it's coming in at 9,900 ohms. Okay, not far off. What's the tolerance? Well, it's got this horrible gold band. And I can't remember what a gold band means, but don't worry, we can look it up. So our resistor had, probably not going to be able to see it on the screen. Maybe I can get it to focus on it. Yes, there we go. It's brown, then black, then orange. Come on, focus on the resistor. Brown, then, all right, move it closer to the middle. Maybe that will convince it. Brown, then black, then orange, then gold. You can't tell that's what it is. You have to take my word for it. Brown, then black, then orange, then gold. So focus now on this. brown, black, so that's 1, 0, orange, that's 1,000, so 10,000, and gold is 5%. Okay, 9,900 is within 5% of 10,000, but I'm going to record that as 10,000 plus or minus 5% as my resistance. So let's write this as R equals 10, and then I'm going to do times 10 to the 3 ohms plus or minus 5%. I'm not going to use the measured value because really I'd want to measure it multiple times in order to get some uncertainty in this, and actually I'll just use what's written on it. And I'm not going to reference the color code, because I mean I could reference the resistor color code table that I used, but it's such a common thing, it's shameful I couldn't remember it, so it doesn't really matter. I could reference it, but I've already got a reference here, and everyone's going to know where that came from anyway. So off we go. We're going to build that circuit. Now, I probably do have a single pole double throw switch, just like I probably do have resistors that aren't mounted on these horrible boards. But I've got 2 prep rooms in this school, and I'm not sure I can be bothered walking across the road to check the other prep room. So I'm just going to use the age-old switching method called shove one banana plug in the back of the other. There's a made switch, there's a broken switch. That's what I'm going to do. When I discharge, it's going to be, sorry, when I charge, I'm going to have to do a slightly different circuit. So when I charge, I'm going to charge through the same resistor. Charge, well, this is discharging. Let's write this as charging. So no E, spelling matters. And what I'm going to do is, first of all, fully discharge the capacitor, making sure that there is no charge in it, like this. And then I'm going to charge it through a resistor. So the voltmeter is going to go across there. This is the other side of that switch. Here's my resistor R, and here's my power supply, like this. Oops, something like that. So I'm measuring the potential difference across only the capacitor, discharge it when I switch the single pole double throw switch that across, it's going to start charging. Current's going this way, it's going to start charging, and I can measure the potential difference across it. Fine, okay, let's produce some tables then. So for charging, what I want is, we'll start with charging. I want the potential difference at different moments in time. So time in seconds and potential difference in volts. That'll do. And how many values shall I get? I don't know. 1, 2, 3, 4, 5, 6, 7. Let's just do 7. No point doing more than that. But I'm leaving space on the right-hand side for me to write extra columns, or draw extra columns as and when I need them. So I won't do the horizontal lines on the table yet. Let's build the circuit. So, big noisy power supply. We're going to use the DC holes. Don't need that turned on yet. I'm not going to, oh well, we could have it quite a high potential difference. Doesn't actually matter. As long as it's not higher than, we could use this voltmeter. So as long as it's not higher than 20 volts, 12 should be fine. Okay, what else have I got? I've got a bunch of crocodile clips, fistful of wires, and those 2. Don't really need anything else. Here's the circuit without the meter or without the shorting wire connected. So you can see I've got the power supply from the positive terminal, which is the red one. The wire comes around and goes into this side. And this side here is the side which is positive because it's the one with the dimple, and the arrow points to the negative side, which then comes around here through the resistor and back to the negative or the 0 terminal of our DC power supply. In order to make sure it's fully discharged, what I have to do is short circuit the capacitor like that. That capacitor is now fully discharged. And lastly, I need to connect up the voltmeter. So I will use 2 more wires with banana plugs and connect the voltmeter up in parallel. Okay, so it looks a bit messy with the wires, and some people like Electronics stuff because they think it's a bit neater. Electronics is the brand that makes the green boards that these things slot into. But I'm fine with it like this because I've drawn the circuit diagram, I've connected it bit by bit, so I know this is working properly. So right now, just move that so there's no glare, there we go. Right now I can touch, this is my flying lead from the positive terminal of the capacitor. I touch the negative terminal to make sure it's fully discharged. When I switch the power supply on, potential difference is gradually increasing. And all I would need to do is take my stopwatch, press go, and every 10 seconds, let's say, every 5 seconds, write down the potential difference. I want 7 readings. If I go every 10 seconds, that's just over a minute. That probably sounds reasonable, although I'm going up to 12 volts. Let's just do a preliminary run through and see how long it takes roughly to get up to a decent sort of potential difference. Yeah, a minute and 20, a minute 30 odd seconds seems to be okay. That gets up to a pretty high value. Let's discharge this. Just be careful you don't accidentally discharge this through yourself because it could sting a bit. That's a safety thing. Yeah, don't connect it back to front. Always double check it, otherwise it could explode. But also, just be a little bit cautious that you are not discharging it through yourself. Should we do every 15 seconds? I'm going to go every 15 seconds. So I'm going to start at 15 seconds. I'm not going to start at 0 because I'm not going to be able to connect it exactly the same time. So I'm not going to record a value at 0 seconds. But I am going to record a value at 15 seconds. Now, usually what I wouldn't do is just write 15. What I would usually do is write 15.00 because I have to record my data to the same number of decimal places as the resolution of my instrument. However, that seems a bit overkill because I'm not going to be able to record the potential difference at exactly that time because this has a refresh rate. Charging up from static in the air by the looks of it or something. Maybe it's still current running through the inductor coils in this. But if I turn that on, look, you can see it's updating, what, 3 times a second? So if it's updating 3 times a second, maybe even 4 times a second, my instrument resolution, really, I can only measure to the nearest quarter of a second. Well, that's still 0.25, so I'm still going to include those 2 decimal places. The other thing I'm going to do that I wouldn't normally do is I'm actually going to fill these in advance because I need to keep an eye on the voltmeter and then write it on here and then an eye on there, and I want to minimize the number of things I've got to do. Now, usually I wouldn't do this. You don't write numbers until you've actually measured them. But actually, I think this is going to be the best thing I can do. So 45 seconds, and then 60 seconds, then 75 seconds, 75, 80, 90 seconds, then 105 seconds. So that's what I'm going to do. Every 15 seconds up to 105 seconds, and I'm going to write them down. And it's a very straightforward practical. So you get to watch me do this, because it doesn't go on for very long. What I'm going to do is make sure it's fully reset, and then hit them at the same time. Actually, I should make sure that's on first. So let's reset that and then press go at the same time. I'm just going to wait 15 seconds. Remember, I'm not writing down the value at 0 seconds because the value at 0 seconds relies on reaction times and all the rest of it. I can't assume it's 0 volts, even though it's a reasonable assumption. Right, so that wasn't paying attention. I got distracted. Let's try that again. Boom. Right, sorry about that false start. This time I'll actually watch the stopwatch. 8, 9, 10, 11, 12, 13, 14, 3.47 I got. You may disagree, but that's what I'm writing. Right, going for 30 seconds. 6, 27, 28, 29, 5.86 I had that time. Again, you may disagree. And I'm going to move my eye from here to here. It's not going to be perfect. 41, 42, 43, 44, 7.84 I think that was. Might have been just before that. And what you can do is set up something to beep every 15 seconds so that you only have to watch this meter. That's quite good. 59, I think that's 9.17. I've done that in the past. I've got a calculator you can program, a DM42, and you program it to bleep. And that's rather wonderful. Coming up to another 15 seconds. I reckon that's 10.20. So that works really well, actually, but there are some disadvantages to that. You need usually a countdown beep, so you're not reacting to the beep. Otherwise, you've got reaction time. 10.98, I think that was. Might have been 10.99. And we're coming up for the last 15 seconds. 11.55. So that gives us a pretty good spread of potential differences on our table. That's charging done. Now let's record discharging. So let's turn that off. Let's fully discharge the capacitor, being very careful not to touch anything, lest we get a nasty shock. Wouldn't be that nasty a shock, but you don't know if you've got a heart condition that's not yet been diagnosed, and you don't want to diagnose it during the lesson. Right, let's fill in the table for discharging, and I'll do discharging on the next page. Just like last time, I'm going to leave some space on the right here. And just like last time, I'll go every 15 seconds, and I will write down the times in advance. But I'm going to change the circuit because this time we're charging first. So let's rebuild the circuit. Here it is, resistor, capacitor, nothing else at the moment. Then we'll connect our voltmeter, which we will connect in parallel with the capacitor. There we go. And then charging using the age-old method of shoving a banana plug in. Actually, we're just going to touch it. So here are my two ends. This is the red hole, which is the positive one in my right hand. But careful now, that's the negative side, is the right-hand side of the capacitor. So I'm going to charge them the other way round, like that. So turn on the power supply, just touch them, bang, straight up to, wow, 20 volts. It's only got a maximum of 25, and straight up to about 20 volts. Let's do it again. Bang. That suggests that this dial is off because it said 12, or more likely, this is a full wave rectified, but not smoothed with a capacitor. So as soon as I put a capacitor in parallel with the supply, it smooths it. But anyway, there we go. That's how we'll charge it up. And then every 15 seconds, we will write down the potential difference. And you don't need to watch me do this again, I don't think, because you've seen me do it once. This time I'll just skip ahead. And there we are. There's my last result. I'm not sure whether I got that one correct. I wrote it down and started doubting myself whether I really saw that number. There's no point taking repeats with this experiment because we're never going to be able to start it at exactly the same time. We are trying to simultaneously start the stopwatch and remove the wire from the capacitor in order to start it discharging. And actually, there's no point trying to get it at exactly the same time. There's really no value in doing that. You might as well just charge it up to whatever it was, nearly 20 volts. Let's put that here so you can see it a bit more clearly. Charge it up to about 20 volts. Then start it discharging and at your leisure hit start. And because we're not recording V0, it doesn't really matter. Or at least it doesn't matter for the discharging, but there is an issue with the charging one. To understand that problem, let's start by analysing the discharge. So when we have discharge of our capacitor, we're looking at V equals V0 e to the minus t divided by RC. That's the capacitor discharge equation that's derived in lessons. Now, we take the natural log of both sides. We end up with the natural log of V is equal to minus 1 over RC multiplied by t plus the natural log of V0. And I've written it like that because that way you can clearly see how y equals mx plus c. We plot that on the y-axis. We've done this plenty of times. And we plot t on the x-axis. Then this term here will become our gradient. And this term here will be our y-intercept. And that's fine. Nothing wrong with that. Equals plus times, put the little symbols in there. So that's very easy to analyze. All we need to do is plot the natural log of v versus t, and then the gradient will be equal to this. And so we can rearrange that equation. We know the value of r to compute the value of c. The problem is with the charging equation. So have I got space on here to show the issue with charging? Yes. The problem with the charging equation is it is V is equal to V naught multiplied by 1 minus e to the minus t over rc. And try as you might, if you don't know V naught, you're not going to get very far with this. So, for example, we might end up with something that looks like the natural log of, how would I write this? The natural log of 1 minus v over v naught, I'm rearranging this in my head, is equal to minus 1 over rc multiplied by t. So you can get from that to that. But there's no way of separating this out. You can't just get the natural log of v by itself. You have to know what v naught is. And we didn't measure it because it wasn't an easy thing to measure. We didn't measure what it was. Now we can assume that it is 0 at 0 seconds with charging, but that's not necessarily the case. Now we're going to start with that. We're going to have to put v naught in as 0. We're going to have to do the analysis. Assume v naught is equal to 0.00 volts. But we don't really know what the uncertainty in that is. But there's no other way around it. So on this table, we are going to have to add a column for the natural log of 1 minus v over v naught. Ah, there's a problem. V naught is not 0. V naught is the value we're charging up to, not 0. It's not the value we start at. The value we start at is v naught when we're discharging. Ah, so that's what we can do. We can use this analysis to determine v0 and then use it in this analysis. We need to measure v naught from discharge, because I did not touch the power supply between our particular measurements. I didn't touch it. Future Keith here, so I did realize my mistake, but right at the end of the video. So keep watching the video right to the end and you'll see I realized the mistake that I made. So that should work. Now in terms of units, that will not have a unit, and v divided by v naught, so the unit of v cancels, so I don't have to put any units up there. That's all I need to put in there, but I've got to do the discharging one first. So I need to put the natural log of v measured in volts here in order to get the y-intercept and use that to determine what v naught is, what this missing value up here is, which I'm not going to assume. So, okay, I guess I'm going to have to do some calculator work. Let's whip out the calculator, type in a bunch of numbers and calculate a bunch of natural logarithms. Now, when you do these calculations, remember that in terms of significant figures, anything before the decimal point is the order of magnitude. But this is in base e, but it's still an order of magnitude. So it doesn't count towards our significant figure tally. So all of, that should be a 7, all of these numbers are actually 4 significant figures, not 5. The first digit isn't a significant figure. Okay, so I've got my numbers. Now I'm going to have to think what am I going to plot, which means I need to think in terms of scales. I'm going from 15 to 105. I could go from 0 to 105. I don't think it's going to make much difference in terms of scale. So, well, let's go with 15. Let's say I need 100. So 10, 20, 30, 40, 50, 60, 70, 80, 90. Whack, that doesn't work. Although 90 would perfectly fit, wouldn't it? 90 seconds. 105 minus 15 is 90. So if I go right to the edge and go 15, 25, 35, 45, 55, 65, 75, 85, 95, 105, that would perfectly fit on the x-axis. What a great choice. Then in the y-axis, we're going from, let's say, half to 3. So half, 1, 1.5, 2, 2.5, 3. That would work. So I can afford to push the x-axis a little bit up, give me room to write things, but I'm afraid I have to have it right to the edge of the paper. So there's my x-axis, and I'm going to label this time in seconds. I haven't actually defined t in my book as time. I think it's obvious, but I should define it. And we're going to go 15, what was it? 15, 20, 25, 30, 35, 40, 45, 50, 55, 60. No, it was 15. What was it? It was 15, 25, 35, 45, 55, 65, 75, 85, 95, 105. 15, 25, 35, 45. We wouldn't normally go up like this, but this makes it fit. So I think it's the most sensible way to do it. 85, 95, 105. We wouldn't really want to go up in tens, but starting from a final digit of 5. But never mind, it works. I should write 0.00, but I'm not going to because there's no point. Now vertical scale. So we've got a false origin. We can't read the y-intercept directly off it. That's, oops, the paper moved. This is why you always rotate the paper before you draw a line. This is going to look terrible now. Always rotate the paper first so you can rest on the paper properly. Look at that. Oh, fail. Oh, that is disgusting. What a terrible line. I'm ashamed of that. Right, so we were going from 0.5 to 1, 2, 3. So 0.5 to 1.0 to 1.5 to 2.0 to 2.5 to 3.0. And I reckon that should give me more than half the page covered in data. And I'll label this axis natural log of V in volts. Okay, now we're going to plot some points. There's my data plotted to the nearest small square. I made a little mistake here, but I don't think you notice it. Looking down the lines, there, it looks pretty straight. There's the line of best fit. Not quite. It's a little bit too high, that, but okay. It's the best line of best fit, perhaps. We could include the worst acceptable line of best fit, which would perhaps be a bit steeper than that. Come in like that, I think. That might be the worst but still acceptable line of best fit. But it's an estimate. So let's call this one the line of best fit, and this one the worst acceptable line of best fit. I can't actually process this data until I've got this graph all analyzed. So we're going to pick some points on the graph. On the line of best fit, I'm going to choose that point looks good. And that point has coordinates 5, 15, so right, 1 second, 15, 16, 17, 18, 19 seconds, and 2.525 volts, and not volts, natural log, so it doesn't have a unit, that. And the line of best fit down here, oh yes, that point there. And that point there has coordinates 100 and so it would be 0.950, 0.950, like that. So I'm going to do the same thing with the worst acceptable line of best fit. So we can get an uncertainty in our gradient. Okay, so that coordinate is 94 and 1.025. And one up here, oh yes, that one, lovely. So that is between 2022 and 2.500. Those are the coordinates. Now I can use them to calculate my gradients. So, line of best fit, gradient. I don't know why I did that. I should put an equal sign. So that's going to be a difference in the y-axis, which is going to be 0.950 subtract 2.525 divided by difference in the x-axis, that's 100 subtract 19. Units of this would be per second. So 0.95 fraction, 0.95 subtract 2.525, and 100 subtract 19, negative 0.0194. Let's have the extra digit, why not? Then we can use that to calculate the intercept. So line of best fit intercept is going to equal the y value. Let's use this one up here. So the y value, so 2.525 subtract negative 0.0194 times 19 is the x value. And that gives me 2.525 plus 0.0194 times 19, 2.8936. Let's call it 4. Let's have 4 significant figures, because why not? Right, then worst acceptable line of best fit gradient. We're going to use these to calculate the uncertainties. So that's going to be 1.025 subtract 2.500 divided by 94 subtract 22. I don't know why students take so long doing this sort of thing. It really doesn't take a long time. 1.025 subtract 2.5 divided by 94 subtract 22. Having said that, I'm bound to make a mistake somewhere. So negative 0.0205, and then the worst acceptable line of best fit intercept is going to be, I'll use the same thing up here, the same point, and project it back with the gradient I've just calculated. So that's the y-axis value, subtract the gradient times the x-axis value. That's just y equals mx plus c rearranged. So that's 2.5 plus 0.0205 times 22. And that's 2.951. So now I've got my gradient and my intercepts. So I can come down here and say gradient is going to equal negative 0.0194 plus or minus, and so we're going to go 0.0194 minus, what's the gradient here, 0.0205 times 10 to the negative 3, so 1, 2, 3, so it's going to be 0.0011, and that's going to be in units of per second. Then the intercept, because I'll need that for the first part of the practical, is going to be at 2.894, doesn't have a unit, plus or minus the difference between these, so 2.951 subtract 2.894, and you can show this working as part of your, well, you can show it in your book if you want to. No units. So there we go. I've got those. And I might as well calculate the percentage uncertainties while I'm at it, because I'll probably need them. So that's 5.7%. And this one here is 0.57 divided by 2.894, 1.96, so 2.0%. And those are the uncertainties. I should probably write down here percentage uncertainty in the gradient and percentage uncertainty in the intercept, just so I remember what those numbers mean. Good. Now, I could calculate what the capacitance is from this one, because that was really what I wanted to do. So capacitance C is going to equal minus 1 divided by R times the gradient, which is going to equal minus 1 divided by the resistance, which was 10,000, 10 times 10 to the 3, times by the gradient, which is negative 0.0194. And that gives me, fingers crossed this comes out as it should, fraction 1, and I could put the minus before it if I wanted to. So 10 times 10 to the power of 3 times, and I'll put this in brackets, negative 0.0194. Let's see if this can handle that order of operations. Okay, so we've actually got 5,154.6 microfarads. That's what that is. That's the same thing. Okay, and the uncertainties, we need to combine them. So the percentage uncertainty in C is going to be 5% from the resistance plus the gradient, so 5.7%. So that's 11%, because we only use two significant figures for this approximation, which gives us an absolute uncertainty in C of 0.11 times ans equals, okay, so I need to think about what that means. 567.0 microfarads, which would only give to two significant figures. That'd be 570 microfarads. So the actual capacitance that we have measured, so let's put measured C is equal to 5,150 plus or minus 570 microfarads. Well, there we are. It was supposed to be 4,700. That is definitely within range. Great success. And we can compare it to our reference and convince ourselves that was true. But now what we need to do is take this intercept and plug it into here. So we're going to use the intercept to determine V0. So V0 is going to equal e to the power of the intercept, which is going to equal, there's the intercept, let's do e to the power of, e to the power of 2.894, 18.065 volts. And the uncertainty in this, right, so let's go with the upper bound and lower bound. So we can say that e to the power of 2.894 plus 0.057 goes as high as 19, which when we minus 18.065 from it would give us plus 1.06 volts. And if we do the minus one, we're going to go e to the power of 2.894 minus 0.057, and then subtract that from 18.065, and we actually get 1.00 volts. So let's go with 1.1 volts. Two significant figures. Let's go with the larger one. So we're going to say that that is equal to 18.1 plus or minus 1.1 volts, which is a percentage uncertainty in V0 of, because we're bound to need that eventually. Remember, it's an estimate. These are asymmetrical uncertainties, and there are better ways of handling them. 6.1%. And we're just going to make a note here, use for charging experiment. So now we go back here. I've now got 18.1. So I now need to calculate this for every single one of those. Right, and there they are. All those are calculated, ready to be plotted. Against t, of course, these are all negative and getting more negative as t increases. So that would give me a negative gradient, but then minus RC, minus 1 over RC is the gradient. So that kind of makes sense. I guess we've got to plot the graph, haven't we? The x-axis scale will be exactly the same as what we had before. The y-axis scale this time goes from about negative 0.2 to just more than 10. Let's say 12, 1.2. So let's go from 2 to 12. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That would fit. So I can afford to start a little bit further down and go right the way across. And this is going to be my x-axis drawn like that and labeled with, just as we had before, 15, 25, 35, 45, 55, 65, 75, 85, 95, and 105, time in seconds. Then the y-axis, we're going from 0.2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we're going to about there. No, I made that mistake last time. Let's turn the page around so I'm leaning on it, so the paper's not going to move while I'm drawing the line. There we are. Insanity is doing the same thing and expecting different results. So we can label this negative 0.2. I should have some more significant figures on that, but I'm going to leave it like that. So negative 0.2, 3, 4, 5, 6, 7, 8, 9, negative 1. Right, so negative 0.3. I keep checking. You notice I keep checking because otherwise I mess things up. I keep checking, otherwise I may have miscounted. Negative 0.7, negative 0.8. Apparently I can't talk and write at the same time without messing it up. 1.1, negative 1.2. There we go. Messed up the number a bit there, but it's okay, it'll do the job. And I'm going to label this axis natural log of 1 minus v over v naught, now that we know what v naught is. Now, because we know what v naught is, we can actually include error bars this time. Couldn't really reasonably use error bars last time. This time we can, but let's just plot the points to start with and calculate a few of the error bars and see if it's worth including them or not. If we can, then we should. So, just check this, plot in these points. So negative 0.21, so that's there. And then at 30, negative 0.39, so that's there. 5, 7. 5, 7 is there. 60 and negative 7, 1 is there. Doesn't take long to plot these. I often say that. It's true. 75.83 is there. And I don't interpolate between grid lines, the minor grid lines, when I plot my points. 90, and that was 0.93. And 105, 1.02. That's there. And that data occupies more than half the page in both directions. Now that looks curved to me. It's supposed to be straight, and that is definitely curved. If you look down it, you can see the obvious curve, which suggests a systematic error. Interesting. A systematic error, which I guess would be V0. It could well be V0. So let's see if the error bars can be used for this. So let's do an upper bound and a lower bound. So let's do positive uncertainty in the natural log of 1 minus v over v0, and the negative uncertainty in the natural log of 1 minus v over v0. And I might not calculate all of these. We'll see if they're worth calculating and worth plotting. I should just finish off my table now because I don't think I'm going to be adding anything else to it. Let's put that there. Right. So let's pick some of these. Which one shall I do? Let's do the first one. So we've got the natural log of 1 minus 3.47 divided by, and it's going to be 18.1 minus 1.1. Oh, sorry. And that gives me that, so it goes up to, or down to, maybe I should have these the other way around. Let's put that in there. And if I subtract 0.213 from it, what's happened there? Answer plus, let's say, negative 0.213. I've got lost in my negatives. That's not right. Let's do that again. Okay. So that's 0.015, which I guess would be this one here, 0.015. Let's do it to the next one, and because the equation is stored in the calculator, I just have to go into here and change the numbers. So that's 391, and then that becomes 391. Yes, it is 391, and that becomes 586. That goes up, 0.032. Right, maybe I will do it for all of these, and then we'll do the other side, uncertainty. So this is negative 0.568. Again, because they're asymmetrical uncertainties, the best way for me to handle it is actually just to calculate the upper and lower bound values. So that gives me 0.050. And I'm not going to read out as I do all of these, because you will get very bored very quickly. 9.17. This is the last one, then I'll do all the rest without reading them out. 706, 0.069. Right, and when I come to this one here, all I'm going to do is subtract the uncertainty. Where is it? Here it is. Subtract the uncertainty rather than add it. At the moment, in the formula on the calculator, you might not be able to see it on the screen, I am subtracting it. I'm doing the other way around. So rather than subtracting, I'll add it to get the other uncertainty, the other side. But I'll carry on doing this for now. I'm doing the last one. Now, perhaps we shouldn't go to this much effort because these are just estimates of uncertainties that we're using. I mean, the uncertainties in the intercept are based on me looking at the line and thinking, oh, that kind of looks okay, but not good enough, which is not really a rigorous approach to working with uncertainties. So these are just estimates, but now we can see that I have to add that much or take that much away. So to the nearest small square, we're talking about adding 2 small squares there and taking away 1 small square there. So this could be that much smaller, that much bigger. And actually, I don't know, I don't feel comfortable with just subtracting that from that. And so that one goes, actually, that would be down 1 and up 2. I'm not sure if I want asymmetrical error bars, but that's what it says. So I'm going to plot these error bars now. So that's going, subtract that so it goes further down. So it goes down by 3, up by 3. They are symmetrical. Lovely. 1, 2, 3. 3 little squares. 1, 2, 3. And this one here is 4 squares down and 5 squares up. So 4 squares down, 5 squares up. They're asymmetrical again. So we're going to have some hefty error bars on this. 6 squares down and 7 up. Wow. And 7 up. So maybe it is straight after all. Might just be straight after all once we incorporate the uncertainties. Or maybe it's such a convincing curve that this is called wishful thinking. Right, so 7 down, 9 up. Right. 7 down and then 9 up. Certainly starting to look like wishful thinking to me. The 90 data point is 9 down and 11 up. 9 down. Takes us to there, I think. Let's just count them. 3, 4, 5, 6, 7, 8, 9. Oh, we've gone too far. 9 down and 11 up. So there, 5, 10, 11, like that. And then, yeah, that's 10 down, 12 up. 10 down and 12 up. So I've now included my error bars. And we can see that we do have a line that passes through the center, well, within all of the error bars. So that would be considered an acceptable line of best fit, just like that, although it just misses that one perhaps. But it pretty much goes through the rest, so I think that's okay. If I completely ignore the error bars, I'd have a line with a gradient about here-ish, but then I'm outside the error bars here and here. So I think this is actually the line of best fit. And the one that ignores the error bars, I think, is the worst acceptable line of best fit. So let's do the same thing we did last time. Let's start with the line of best fit gradient. Let's do that calculation. I need to pick some points first, don't I? So on the line of best fit, shall I use, where's my red pen? There it is. Let's use my red pen. Line of best fit. That's a nice point there. That is 103 by negative 1.09. And up here somewhere, looking for a nice point where it crosses the grid lines. It doesn't really cross any grid lines in nice convenient places. The closest is probably that one there. Still more than 8 centimeters vertically and horizontally, so it's still acceptable. It's just I usually prefer it to be a bit further out, but never mind. So it's 48 and negative 0.53. And then for our worst acceptable line of best fit, it goes right through there, which is lovely. That's 100 and negative 1.00. And it goes through, come on, pick a nice point. That point there, which is 19 and negative 0.28. So we've got our points now, where we would calculate our gradients. So our gradient is the difference in the y-axis, so negative 1.09 subtract negative 0.53 divided by the difference in the x-axis, so 103 subtract 48. Calculator. So negative 1.09 subtract negative 0.53. And 103 subtract 48 gives me negative 0.0102. Might as well do 3 significant figures. Although I don't know where I'm going to be rounding it. I'll tell you what, let's put 189 or something like that, because there's a recurring dot over the 1 and the 8, so actually that'd be 182, wouldn't it? 10182. There we go. Then I'm going to do the intercept. So intercept is going to be the y value. Let's use this one up here. So negative 0.28 minus the gradient. So that's 0.010182 times the x value. So do I need the gradient, the intercept? Probably not, actually. It should actually be equal to 0. Let's find out. 0.001082 times 19 is, oops, I cleared it. Negative 0.28 plus 0.010182 times 19 should be equal to 0. We get, well, it's not quite 0. Not far off, but it's not quite 0. 0.865. And that would have no units. The gradient would have units, though. The gradient would be in units of changing y divided by changing x, so second to the minus 1. Right, now the worst acceptable line of best fit gradient. So that's going to be negative 1.00, subtract negative 0.28, divided by 100, subtract 19, which is, let's just get the fraction there, so too many, minus 1.00, I don't know why I typed the 0.00, subtract negative 0.28, divided by 100 minus 19 is equal to negative 0.00889, I guess, if we want to record it to 4 significant figures. Doesn't really matter, we're going to round them away eventually. And the intercept, the worst acceptable line of best fit intercept, which we don't really need for this, but we'll do it anyway, is, I used the wrong point to calculate the intercept there. Look at that. I used the wrong point. I used the green one, and I should have used the red one. The red one's the line of best fit. I did that wrong. It should be equal to, what a fool, should be equal to negative 0.53, subtract the gradient, so that's subtract minus 0.010182 times 48. It's still not equal to 0, but it should be. So it's closer to 0 than it would have been. 26, something like that. It's closer to 0. So the intercept for this one, that one is going to be the negative 0.28 subtract negative 0.008889, and then times by 19. And this is where we find out the worst acceptable line of best fit is actually better. Hopefully not. Negative 28 subtract negative 0.008889 times 19 is, crikey, what have I done wrong there? I can't see anything I've done wrong. Oh, I think I know. I wrote 28, not 0.28. Oof. I thought that was very wrong. Negative 0.1111 something. So, yeah, the worst acceptable line of best fit does give a intercept which is further from the 0, further from the origin, and therefore, yeah, the worst acceptable line of best fit is worse than the line of best fit. But it doesn't matter, because that's going to give us our values for, have I got any room to write this? No, I'm going to have to put it at the bottom here. That's going to give us our capacitance for this one. So our capacitance, spell it right, C is going to be equal to, that's going to be equal to minus 1 over r times the gradient, which is equal to, we're going to use this gradient here, so minus or negative 1 divided by our resistance, which was 10 times 10 to the 3, times by our gradient, which was, put it in brackets, negative 0.010182, giving us a much bigger number than we wanted, about 9,821 microfarads. It's like twice as much as it should have been. That's not good, is it? Oh, well, that's what it says. Let's do the uncertainties and see if that mops up some of the nonsense here, because that's about twice as big as it should be. So the uncertainty in the capacitance is going to be equal to the uncertainty in the gradient plus the uncertainty in the resistance. The uncertainty in the gradient is going to be, let's just do the difference between these. So 0.008889 minus 0.010182, and then divide that by 0.010182, and that gives me 12.7%-ish plus 5%. So we're on about sort of 18% uncertainty. Yeah, that's not going to work at all. 18% uncertainty, 9821 times by 0.18 is that. So our capacitance is 9800 plus or minus 1800 microfarads. Yeah, that didn't work at all. The lower bound for that, I need a calculator for that, is 8,000. The discharge practical got us a number that was within tolerance. The charging practical, I don't know what's gone wrong there. I'm sure you can pick it apart yourself later on and spot some rather dozy mistake I've made. But clearly the capacitance here, we were doing the experiment to measure the capacitance. I relied on a value from the discharge experiment to calculate the capacitance from the charging experiment. V0 should have been the same for both. So I should just be able to carry V0 from one experiment over to the other. But clearly something was awry. And I've just remembered what. The V0 from this is not the same, because the V0 from this, it had already started discharging before I started the stopwatch. So this V0 is much lower than the V0 for this experiment, much lower. If our V0 is much lower, this fraction here is, this is bigger, so 1 minus a bigger number is a smaller number, so we're taking the natural log of a, here we are, taking the natural log of a smaller number all the way down here. All these are wrong, and by a consistent amount. So it is a systematic error given as a curve, which is why that's rubbish. And you could always write that in as a conclusion somewhere. The reason why that's rubbish, that moment of realization that came just a bit too late. The V0 in this equation, what we were charging up to, was the full terminal potential difference of the power supply. When we discharged, I started the timer, so t equals 0, after the capacitor had already started discharging. So that value there is incorrect. The V0 on this equation is not the V0 in this equation. Well, you live and learn. Hopefully you found that a useful experience, and maybe next time it would have been worth me actually starting the stopwatch and disconnecting the capacitor at exactly the same time, because then I could have carried that V0 over to here, and then the results would have come out okay. How frustrating. I'm not going to do the whole video again. I'm happy leaving the mistake in there because it's a learning point for everyone. I'll make these mistakes so you don't have to. The other thing is I would start with discharging and then do charging. I'll do these two the other way round for obvious reasons. Hopefully you've got something useful out of that video.